started. The first is partial state archival cap62, and then in-memory Soroban state for cap66. And no, Tomer, I will never stop using eccentric Linux distro. Cool. So I guess before I get started, I guess a little bit of background. So Protocol 23 is kind of where the rubber is going to start hitting the road as far as state archival is concerned. So kind of some background to when Soroban launched, we of course had the interface for state archival with rent and all this sort of stuff, with the intention that eventually entries that have run out of rent will be archived and then removed from validators in order to free up space, so you don't have the issues that come with large amounts of state that have to be maintained. And so that's kind of where we're going. Now today, the interface is such that you still pay rent, you still have to issue restores and all those sort of things. But the data is not actually yet removed from validators. And so that's where we're going. So initially, the plan was for Protocol 23 was to have what we're calling full state archival. And in full state archival, what happens is entries, once they have run out of rent, be removed from the live state, and then they are added to this temporary data store called the hot archive. And the hot archive is still maintained by all validators, but it's just a separate database that just maintains entries that have been recently archived. The thinking being was that eventually this hot archive would become full, and when the hot archive is full, what you would do is you would create a Merkle tree of that data. Validators would maintain the Merkle root and then delete all the information in the hot archive. And then you would just repeat this process iteratively. So essentially, you evict entries from the live state to the hot archive state. Eventually, that hot archive cache will become full, and then you'll actually delete and remove those entries from the validator. And then the restoration process, once an entry has been archived in this way, if it no longer lives in the validator, there's like a Merkle-style proving scheme to which you are able to restore an entry back to the live ledger state. So that's kind of what we consider full state archival, which is where entries actually get deleted from validators. But thinking about this problem a little bit more and looking at the current metrics of Soroban, it seems that we're still a little too early for this full state archival. I think long term, if you look at smart contract platforms that have large amounts of state, there are significant issues with maintaining all of that state. You have lots of hardware requirements on a network like Solana to maintain large amounts of caches. And then you have networks like Ethereum that don't have large hardware requirements, but they're very slow just due to maintaining these very large databases. So long term, at scale, I think it's still very important to have the full state archival solution where entries are deleted from validators and then restored via proving schemes. But the reality of the situation is we're not quite there yet. And I think that currently there is less than a gigabyte of Soroban state currently live on Stellar. And so going through all these hoops and adding all this complexity for this proving scheme just to delete a small amount of data isn't really worthwhile at this point. And so that's why for Protocol 23, instead of going the full state archival route where we actually delete entries, we are doing something I'm proposing something called partial state archival. And this is what cap62 kind of explains. And so in partial state archival, what we do is we do kind of the first half of the full state archival. So we still maintain two different databases on the validator. You have the live bucket list, which contains all of your live state, which is the ledger as it exists today. And then you still have a what's called the hot archive, which is a cache of recently archived entries. And so what you would do is that whenever an entry runs out of rent, it would be evicted and removed from the live state and added to this hot archive database. Now, the key distinction here with partial state archival is even though you still remove things from the live bucket list and add them to the hot archive, you never actually delete the hot archive. The hot archive never becomes full, such that the entries are never actually removed from validators. And so it's partial state archival because you are still kind of storing live state in one database and storing archive state in a different database, but you're not actually removing any state from validators. And so I think my current proposal would be in Protocol 23 to implement the partial state archival with the intention of later on in the future extending this to the full state archival solution. The only reason is that I think that for the the size at which the hot archive becomes full and becomes deleted is configurable. And so I think we could do something reasonable, such as we could implement this state archival solution, but we could set the capacity of the hot archive to something very high, like 50 gigabytes, such that it would take a long time and a lot of network activity to actually start deleting state. And then, if the network was to grow that much, such that we had 50 gigabytes of archived Soroban state, then it would actually make more sense to start deleting state and requiring proofs for all the operational benefit that we get there. And so that's kind of the current proposal of 62, is we're going to still maintain all information on the validators, but we're just going to move archived information from one database to a different database. Now, the reason that we want to do this separation of archive state and live state is that it actually opens up a large number of optimizations. And so that's what we get into in CAP 66, which is in-memory Soroban state. And so we can, because we have the system where the live state or the live bucket list holds all classic information and all live Soroban information, and then we have a completely separate database that stores all the archive state. Now, because of the rent system and because of the way that we do write fees, where a write fee is a function of the total size of the bucket list, we actually have a way to put a soft limit on the amount of live Soroban state at all times. The reason being is that, with the current bucket list size, if you were to add enough live state such that you go beyond the target bucket list size, writes become very, very expensive, such that the network users are incentivized to allow entries to run out of rent and become archived. And so because of the way our fee system works, we have a way to essentially have a soft limit on the amount of state in the live bucket list at all times. And so what I'm proposing is to change that fee slightly, such that instead of the Soroban write fee corresponding to the size of the entire live ledger of both classic and Soroban entries, it only applies to the live Soroban entries. And so essentially the bucket list target size, instead of being a bucket list size, would change to just be the live Soroban target size. And I think this is much more fair, given that classic entries don't actually have to pay rent yet. And so it's a little unfair that adding classic entries actually changes the write fees and the rent fees for Soroban. And especially as the network exists today, classic state dominates Soroban state size. And so changes in Soroban usage don't actually really affect Soroban write fees. Rather, changes in classic usage affect Soroban write fees. And so by changing the bucket list target size to Soroban state instead of just all total state, we have a much more fair fee system. But what that also allows us to do is to prioritize live Soroban state above archive state. So what do I mean by that? So if we change the way that we calculate fees to only look at Soroban size, we can use the fee system to enforce a maximum amount of live state at any time. So for instance, we could set the target Soroban state size to 1 gigabyte, and then the fee system would ensure that there's not much more than 1 gigabyte of live Soroban state at any given point. Now you could maybe, go a little bit above that if people are willing to pay expensive fees. But the way that the fee growth works is that, you are reasonably capped to a small amount of state. And so because we have the system where the amount of live Soroban state at any given time is fixed, what we can actually do is just store all Soroban state in memory and not have disk access at all. And so that's the current proposal in CAP 66, is to prioritize all live Soroban state in memory. And this is made possible because we store live Soroban state in one database and archived state in a different database. And so by splitting the state into two separate databases, we can very easily just iterate over the live database and store all that Soroban state in memory. And so that's kind of what's happening behind the scenes as to what the validator is doing. Now we're able to do this because of the maximum Soroban state size. if we didn't have this, and if Soroban Live State was able to grow unboundedly, this would be a very dangerous optimization because validators might run out of RAM. But because of the state archival system, we can actually fix the amount of live state, and so there's no runaway RAM risk, and so we can very reasonably store all Soroban state in memory. And so there are some changes we need to make to the developer experience and the user experience to make this possible. So first, we are going to change some of the resource types a little bit. So currently, today, we only have one read resource, which is read bytes and read entries. And this assumes that all the information you're reading is on disk. And so what we're going to do, or what CAP66 proposes, is to split this into two different resource types. So they're going to be an explicit in-memory read resource, and then an explicit on-disk read resource. Now, the reason we're doing this is that even though all Soroban state is, or all live Soroban state is held in memory, Soroban contracts can still access classic state, and classic state needs to be on disk. Now, because classic entries aren't subject to state archival, they have the runaway RAM risk, and so we can't store classic entries in memory. And so Soroban contracts will still have to pay disk fees for classic state that's accessed. Additionally, we're only storing live state in memory. And so if you access archive state, for example, a restore operation, then you would still have to do disk reads. And so there's a disk fee for that. But essentially what would be changed is that you would, there would be a network limit for the maximum number of on-disk read entries, as well as the maximum number of in-memory read entries. Now, that being said, because the in-memory reads are a lot cheaper than the on-disk reads, we can actually pass a lot of that savings down to the user. So in this proposal, there would actually be no in-memory read bytes limit. So essentially, the read limit for live Soroban state would just completely go away because in-memory reads are cheap, and so there's no reason to limit that. Now, we would still limit the total number of entries being read, but the bytes being read would not be limited. Additionally, because we're not doing disk access, there would no longer be a read fee associated with accessing Soroban state. And so because you still have to pay like an instruction, like CPU count and things like that to actually process large amounts of data, but because we're not going to disk, there doesn't need to be an explicit fee or resource for that. And so essentially, for live Soroban state, you don't have to pay for reads, and you can read as many bytes as you want. You still have to pay for the CPU though. So it's still an implicit fee, but there's no explicit read fee. And so that's kind of the first advantage to the in-memory versus on-disk resource. Now, the second thing this allows us to do is also implement auto-restore functionality. And so previously, when we first launched Soroban, we weren't sure what the final state archival proof system was going to look like. And so while from a technical standpoint, there was no reason to require a separate restore operation and a separate invoke host function operation, we did that just to give us flexibility later on in case the proof system turned out to be very involved. But in CAP57, we've actually outlined a pretty lightweight proof system that works with invoke host function. And so what we're going to do is in CAP66 is we're going to allow automatic restore. And so what this means is that you no longer will have to issue a restore operation prior to your invoke host function, but actually your invoke host function operation will just automatically restore any archive keys that are in the footprint. And so this reduces the transaction count required, reduces fees, and should just offer a much better user experience. Now, the way this works in resources, though, is that, like I mentioned before, the live Soroban state is all cached in memory in one database, and archive state is uncached and on disk in a separate database. And so if you call invoke host function and every entry you're using is currently live, then you would have the free in-memory resource bytes, and you wouldn't have to pay for disk. That being said, if you're using automatic restore, the entries being restored would come out of the disk read bytes and would be charged disk fees because, again, for the entries that are archived and live in the hot archive database, those do have to be read off of disk. And so I think that's kind of at the high level of what we're proposing. kind of the TLDR, because I've been talking for a little bit, is that Cap50 archived entries live in their own database, and live Soroban state lives in the separate date or a live database. We are then going to cache all the Soroban state in the live database. In order to pass that savings on to you, there will be an in-memory read byte limit and an on-disk read byte limit and fee. And then finally, there will be automatic restore to essentially remove the need for the restore operation in most cases. So I guess, are there any questions or any conversation points we'd like to touch on more?
It looks like there's a question in the chat box about I think a lot of dApps extend TTL by default. Will that still be necessary?
Yeah. So I think so just because we have automatic restore doesn't mean that you don't want to still manage your TTL. And so, like I managed before, if all the entries that you're using are currently live, then then you don't have to pay read fees, and you have much larger read limits. And so you are still incentivized to pay rent. But the issue is when you restore something, you have to pay write fees for the restoration, and you also have to pay disk read fees for the restoration. And so I think from a fees perspective, if you're using an entry a lot, it's still in your best interest to extend the TTL to save money. As even because the restore is automatic does not mean it's free, and so you still have to pay for that restore. And even if it's the same invoke host function, an invoke host function invoking a function that only accesses live state is significantly less expensive than invoking a host function that has a automatic restore on the front end of that. So we still definitely want to extend TTL. Yeah, let's see. So for orbit lens, will it be possible to tell in advance whether the entry will be automatically restored during the simulation? Yes. And so this is kind of more of the implementation details, which are included in the CAP. But what we're doing is Captive Core has recently added a couple of HTTP endpoints for querying ledger state that will be used by RPC in order to simulate transactions correctly. And so essentially this endpoint is a high performance, multi-thread HTTP endpoint that has a similar performance to SQL table queries. And so it should be appropriate for production use cases. And what this endpoint will do is to key value search, where for every key you provide it, it will tell you if that key exists, and then if it exists, it'll give you the value. And then it will also give you meta information about that key. And so it will give you the ledger entry. It will tell you if it's live or archived. And then it will also tell you, what its current TTL value is, and if it's in memory or on disk. And so the Captive Core endpoint is kind of expected to be the new kind of entry point for this information. And so you should be able to query the current archival state and the current in-memory versus on-disk state of any entry directly via Captive Core. Again, there's also meta that we're emitting for all these events. So if you wanted to, it's theoretically possible to ingest meta and maintain the state of Soroban entries that way. But if you don't want to do that and create your own SQL table and pipeline, ingestion pipeline, you can just use the Captive Core HTTP endpoints. So will automatic restore become automatically available for existing contracts? Yes. So this is all handled at the RPC level. And so essentially what's changing is that with Protocol 23, and this is detailed in CAP 66 specifically, is that we are changing the footprint to have this field where you distinguish in the footprint if a Soroban key is either in memory or on disk. And so essentially what the validators will do is that for whenever they receive and apply an invoke host function, they will look at the footprint, and for every Soroban entry that is marked as being on disk, aka marked as being archived, before running that transaction, the validator will essentially restore those entries automatically. And so the actual contract and the contract logic will not change, which means that all deployed contracts are automatically compatible with this. Now, the invocations to those contracts will change slightly because of the footprint changes. But again, this will all be handled by RPC. And so pre-flight will do all this automatically. Let's see, other questions. Oh, so ledger streaming mode. I'm not sure about the context, but behind enabling or disallowing meta streams on validators versus captive core instances. I imagine it has to do with performance reasons, where you don't want ingestion to make a validator fall out of sync. And essentially, that config setting is an opinionated way of saying that validators should be high performance and never get blocked. Whereas, like a watcher node that's not participating in validation would be more appropriate for observing and adjusting the meta because there's not, it doesn't depend on a downstream system. Where if the meta stream gets clogged because the downstream system isn't adjusting fast enough, you wouldn't want to lose sync and have a validating node fall off the network because of a downstream issue. Cool. So I guess
So
I'll
there's another
if there's
question from George about how the cap mentioned somewhere that auto restore won't always be possible. Can you elaborate on these scenarios?
yes, okay. Thank you for pointing this out. So there are a couple of edge cases where an invocation will still require an explicit restore operation. Um, sorry. And so essentially, because the in-memory reads are so much cheaper, um, they don't have limits like the on-disk read, the on-disk do. While there is no read bytes limit at all, and while there is an entry read limit, the expectation is that this limit will be significantly higher than the disk limits. And so, just for example, suppose that in Protocol 23, the transaction in memory read limit is 40 entries, and the on disk read limit is 20 entries. And so, say you have like this DEX trade that will access 40 Soroban entries. Now, if all of those entries are live, then it's within the limits. The invocation works no problem. But say that all 40 of those entries are archived. Now, even though the in-memory limits are large enough for that transaction to succeed, you can only the automatic restorations will come from the on-disk limits. And so, because you have to pay disk fees and are subject to the disk limits for the restore operation, you can only restore, in this example, 20 entries automatically, even though you need to have all 40 to be live to complete this DEX trade operation. And so, in this scenario, you would need to still manually submit a restore operation, just because the way that the limits are set, you can't fit that many restores in a single transaction. Now, that being said, especially given some other exciting work that's happening in 23, we expect to raise limits pretty significantly across the board. And so I suspect that this edge case will not affect most transactions. It will only affect very expensive transactions that are doing a bunch of stuff. And so, for instance, if you have a DEX trade and it's trading assets that are mostly live, you won't be affected. Really, you're only going to be affected um, if you have like a DEX trade that's crossing a ton of orders, and for some reason, all those orders were archived.
So you mentioned that the restore op could be deprecated because of the automatic restore, but this edge case requires you to keep something like that around, right?
Yeah, so I think I mentioned the cap that we might want to deprecate the restore op. And that's just because that if the footprint is automatically restored, um, then having both the restore op and the extend TTL op is kind of redundant. Because, for instance, say that you just want to restore something, you don't actually need two operation types. You could just essentially use the extend TTL, put all the keys you want to restore in the footprint, and then just set the TTL extension to 0. And this is functionally equivalent to the restore op. And so when I mention deprecating the restore op, I don't mean deprecating the ability to restore transaction or to restore entries via an explicit transaction, but I just mean like, mechanically, do we need both the restore op and the extend TTL op? Where the extend TTL op could now, in theory at least, both do a restoration as well as extend.
Okay, yeah, that makes sense. Nico had a question about how the Soroban state size is initialized at upgrade time. It's not specified in the cap.
Yeah, I think I need to expand on this a little bit more. So I think part of this cap is that we are changing the semantic meaning of a network config setting. So in particular, the bucket list target size will become the Soroban state size. Now the issue is currently the bucket list is like 11 or 12 gigabytes, and so we all of our network settings are assuming that your target size is like 13 gigs. But now the issue is if we do a protocol upgrade, protocol upgrades previously have never actually changed config settings, and so if we just do the protocol upgrade, all of a sudden, instead of your baseline for fees being 12 gigs with a target for 13 gigs, because we're only tracking Soroban state, your target is still 13 gigs, but now your baseline is like 400 megabytes because there's like a lot less Soroban state compared to live state. And then you have this DOS attack where until you upgrade the network config settings, you essentially have no read or write fees for both in-memory and on-disk state. And so you could have like a DOS attack where someone writes like tons and tons and tons of temporary entries and like, spams the ledger for essentially 0 fees. And so I think what I'm proposing is that, currently there's like an operational lag between upgrades because core validators can only queue one upgrade at a time. And so you'd have to get all of tier 1 to ARM for the protocol 23 upgrade. And then after that goes through, have them all ARM for the network config setting upgrade. And in between that time, you have free reads and free writes, which is a huge security risk. And so what I'm proposing is that because protocol 23 is semantically changing what this config setting means, the protocol upgrade itself should also change the value. And so this is slightly different implementation-wise than what we've done previously, but I think it should be relatively straightforward implementation. Whereas like the protocol 23 upgrade, both semantically changes what the bucket list target size means, as well as it resets it to a initial starting value that's more reasonable given this new interpretation of the data.
Yeah, that makes
Okay,
sense.
so
We've actually updated settings on protocol upgrades before. I think we know that works.
Oh, cool. Okay, great. Let's see a couple other questions. Okay, so for Orbit Lens, the storage for the hot archive. Yes, so the hot archive and the live bucket list are both part of consensus. So we need the hash of that state. And so for that reason, both of the live database and the hot archive database are both bucket list DB implementations. And that's just because we have to merkleize those structures. And bucket list DB is pretty fast these days. Now, with respect to offering tables to bucket list DB, we don't really have any plans to do that. And the reason is it's a very difficult structure to add tables to. So it's a log structured merge tree, which is kind of a variant of like database used by like RocksDB or LevelsDB. And it's also completely made in-house. Like we didn't fork Levels, we didn't fork Rocks or anything like that. And so kind of we have it works very well for query types that the validators require, and it's very efficient at those. But we have to essentially like handwrite C++ optimized code for those specific queries. And so it would be both a very significant undertaking to allow arbitrary index types for downstream. And it would also probably not be a very efficient database just because it's a locked structured merge tree. And so a SQL style index query would not work very well on it. And so I think what I'd like to do with this is, we've for arbitrary key value lookups, we have exposed endpoints that are on the same scale as SQL queries. But again, they're just raw key value stores. They're not indexes or really tables. And I think there's been a lot of work done by the platform folks on the CDP and things like that. And so I think given that the complexity of the database of Stellar Core is increasing a lot, and for a variety of reasons, we only support Buckless DB now and no longer support SQL. I think that any sort of raw database access needs to move more in the direction of utilizing downstream, utilizing meta ingestion, utilizing CDP, and not rely on direct access to course databases. Just because nowadays with Buckless DB, the core database is very specialized and is not suitable for generic queries. Cool. I think there's a couple people typing, so I'll let them finish. Or if anyone else has any other questions. If not, I have a third cap that I'd like to introduce. I'll give it a second and then we can move on. All right, I feel like we've had enough time. Oh, answer about SLP 001. Dialects, would you mind linking that question again? I'm not quite sure what the SLP 001 question is. Oh, yeah, the new limits. Sorry. Yeah. Cool. So I guess now I'd like to move on to CAP 65, the reusable module cache. And so, like I mentioned before, we were doing all this optimization stuff for in-memory state. And essentially, in addition to saving all of the contract data in memory, we can also save all of the contract code and by extension, all of the contract modules in memory. Because we have a way of archiving contract instances and contract code that hasn't been read recently. And so with that, I think Graydon's on the call if you want to come up and talk about CAP 65.
I don't think Graydon's on the call. I believe we were going to speak about CAF 65 next week, right?
Oh, sorry. I guess I gave y'all a little teaser for next week then. My apologies, got a little ahead of the gun. But so yeah, so I don't want to steal Graydon's thunder, so I'll just leave you with the teaser that we can have lots of this not only helps optimize the read limits, but also optimize the CPU utilization as well. But we'll talk about that more later.
All right. Unless there are any other questions, we can conclude this meeting. Thanks, Garen. It was a great talk.
All right, thank you. And if y'all have any more questions or concerns, there's a couple of discussion tabs on the caps, or just ping me on Discord.